Okay? And so when we look at delta T, it's the change in the time from when we start the reaction to when the end of the reaction happens. It's the change in, or not time, temperature. So when you put your thermometer in the calorimeter and then you get a baseline temperature and then the reaction starts, the temperature is either going to go up, i.e. it's being released, or the temperature is going to go down, i.e. energy is being consumed. Yes, Riley? Temperature is in degrees Celsius because of this very specific thing right here. Okay, good question. Degrees Celsius. So thermal energy, what you can't read because of the glare of the light, thermal energy is a measure of kinetic energy. How do we solve kinetic energy? Do you remember?
1/2 mv².
Right. All right, specific heat capacity. This is important that you understand this, highlight it, put stars around it, make it look pretty. Somebody took my highlighter, Riley.
No.
It's the ability to raise the temperature of 1 gram of substance by 1 degree Celsius. Okay? Which is the unit. It's the energy that is required to raise 1 gram of substance 1 degree Celsius. If something has a large specific heat capacity, it's going to require a large amount of energy to be transferred. If the specific heat capacity varies for each different substance, and we can find that on page 3. Nope, page 3 of our data book. So this is the specific heat capacity for air, 1.01 joules per gram degree Celsius. This is for a polystyrene cup. Fancy word for styrofoam, right? There's polystyrene. Look at that. It must be a polymer. Copper, 0.385, aluminum, 0.897, iron, 0.449, tin, and water, 4.19. It takes a ton of energy to raise water 1 degree. 1 gram of water, 1 degree. And remember, 1 gram of water is equal to
1 mole.
milliliter is equal to 1 cubic centimeter. So 1 gram is equal to 1 meter, milliliter is equal to 1 cubic centimeter. Okay? So that's where these numbers are. Whoops. Just got to fix that book. Okay? All right. This is just a bunch of information. Oh. Let's work on. Okay, so calorimetry is an actual physical way of measuring the amount of energy change in an isolated system. And so it's a process that's used to measure the heat released or the heat absorbed by the reaction. And it's carried out in a calorimeter. Now, how this works is it needs to be an isolated system. So if you remember, an isolated system, neither energy nor matter can leave. And we need to get it in real world, we need to get as close to an isolated system as possible. And there's two things that we look at. So the chemical system, which are the reactants, is placed inside the calorimeter, and then what's around the calorimeter is a known amount of liquid, which is usually water because it has that high specific heat capacity. So it takes a large amount of energy to change that place. So we have a chemical system. And then we have the surrounding. Okay. And so as the reaction occurs, the potential energy of the chemical bonds is converted into kinetic energy. So we see that change of kinetic energy by the change in temperature. And there's always an assumption that the calorimeter is an isolated system and that all of the energy is being transferred either inside the reaction or to the surrounding liquid. So if we were to look at it, what we call a simple calorimeter, this is just a standard beaker with two styrofoam cups. And so our reactants are going to be here inside of this calorimeter. And then we put a thermometer through the top of the styrofoam cup that's upside down. And we mix our reactants, we seal this up, and in here, this is the water that's surrounding the system. So you have three polystyrene cups, a measured quantity of water, and a thermometer. Okay, so this particular one has a system that looks like this with a cover on it. And then this sits inside of another styrofoam cup. That's what they're explaining here. A measured quantity of water and a thermometer. So the chemical system is placed or dissolved in the calorimeter. So this is where the chemical system is. And then out here is the surrounding. Okay? Energy transfers between the chemical system and the surrounding water are monitored by measuring the change in the water temperature. We can analyze that energy change from a calorimeter, and the things that we need to look at is whether the system is exothermic. And so what happens is the chemical system loses that energy to the surroundings, causing the surroundings to gain energy. We see that increase in the thermometer. Or the chemical system takes energy. So in the first one, the chemical system releases energy. And in the second one, the chemical system takes in energy, and that would be endothermic. The chemical potential lost by the chemical system is equal to the kinetic energy gained by the surrounding liquid. And so here we have the chemical system where we have E potential is equal to negative kinetic energy. We have the enthalpy change is equal to the negative thermal energy. And so therefore, we can say that moles times our molar enthalpy is equal to negative mc delta T. So Q is the surroundings, and that's why we draw this T table, right? This is chemical system, and this is surroundings. And in the surroundings, we have Q, negative Q, and in the chemical system, we have delta H. Where we have delta H, we have this beautiful formula. And where we have negative Q, we have negative mc delta T. And I put it in brackets to show you that this system here, we originally learned it as this. And so the negative is just being carried down from the Q being negative. And this is the piece that I was talking about yesterday. 1 ml of water is equal to 100 grams of water. Because our specific heat has a very specific unit, it's joules per gram degree Celsius, we always have to make sure that our energy is in joules and our masses are in grams. N is the number of moles of the chemical undergoing the reaction. And then delta RH is the molar enthalpy. And remember that the other day we worked completely with kilojoules. And so you would have to convert kilojoules per mole is equal to 1,000 joules per mole. Okay, so we need to do those memory pieces. And so this is what it would look like if we did it in a diagram. If we were looking at exothermic, we would have our chamber, and it would be sealed because it's an isolated system. And in here, we would have our thermometer. This piece here, this is our chemical system. This is the chemical reaction. And this is a negative delta H. If it's exothermic, delta H is negative. So that would mean that the energy would leave the chemical reaction and go into the surroundings. Because this is a negative delta H, here we say delta H is equal to negative Q. So if delta H is negative, then Q will be positive. If we were looking at an endothermic system, we know that that is energy absorbed. Again, this is an isolated system, so everything would be sealed. We would not be losing energy or matter. We would have our thermometer. And here the temperature would be high. I forgot to fill in the thermometer. We would see an increase in temperature. So here's our chemical reaction. And it will have a positive enthalpy change, and it will take energy from the surroundings to help it support that. And so then we would have a negative Q, and we would see a decrease in T. Okay, this surrounding area in here, this is all in here, this is water. And same with this here. So let's look at an example of what this looks like and how we can decode the questions. And so a 0.61 gram sample of ethanol is burned, and all the heat released is absorbed by 75.42 grams of water. The temperature of the water rises from 26.9 degrees Celsius to 41.2 degrees Celsius. Use this information to calculate the molar heat of combustion of ethanol. So we need to start out with identifying our information in this problem. So we have our chemical system, our reaction, and we have our surroundings. So in our surroundings, we have 75.42 grams of water, right? Our surroundings is our water, and our chemical reaction is our combustion of ethanol, right? Burned, this is combustion. We have the initial temperature of the water starts at 26.9 degrees Celsius, rises to 41.2 degrees Celsius, and we know that the specific heat of water is 4.19 joules per gram degrees Celsius. On the ethanol side, we know that the mass is 0.160 grams, and we're looking for the molar heat of combustion. So this is what we have. In a chemical system, we have delta H, and in a surroundings, we have Q. So this we solve by N delta RH, and this we solve by negative MC delta T. So if we want to isolate for delta RH, which is what it's asking us to find, the molar enthalpy of the molar heat. So this is molar. then we can go delta RH is equal to negative MC delta T divided by N. Now we have M of this piece here. We have C. We have delta T. What we don't have is the N from this side. So in order to solve the number of moles, we need the mass divided by the molar mass. And so we got 0.160 grams divided by, and we look at methanol, it's 2 carbons, 5 hydrogens, 1 oxygen, and 1 hydrogen. So 24.02, 5.05, 16.0, and 1.01. And we should get 8, 0, 7, 12, 16, 3, 4. We should get 46.08 grams per mole. So delta RH is equal to the negative of 75.42 grams multiplied by 4.19 joules per gram degree Celsius multiplied by delta T is going to be equal to 41.2 minus 26.9. And then we're going to divide all that by our number of moles, which we determined to be 0.003472 moles. So delta RH is equal to negative, carrying from here, 1.3014 times 10 to the 6 joules. So when we do our canceling, grams cancel out, degrees Celsius cancels out, we're left with joules per mole. And so we can look at our answer in one of two ways. Negative 1.30 times 10 to the 6 joules per mole, or negative 1.30 times 10 to the 3 kilojoules per mole, which is the more standard way that we see it. Either or, your answer is acceptable, and the negative coincides with what we know about combustion, and most times combustion is exothermic. Now, when we look at question number 2, what did I do? A sample of NH4 of ammonium nitrate having a mass of 30.5 grams is dissolved. Okay, a sample of ammonium nitrate having a mass of 30.5 grams is dissolved in water in an insulated cup to make 500 mils of solution. The heat of solution is 25.7 kilojoules per mole. Will the solution increase or decrease in temperature during the dissolving process? Well, we need to look at the question. The heat of the solution is positive 25.7 kilojoules per mole. And what do we know the positive symbol to be? But endothermic. So it will decrease in temperature because it's endothermic. Okay? If the initial temperature of the water is 21.5 degrees Celsius, determine the final temperature after dissolving process is complete. Assume no loss of heat to the surroundings. There's a keyword. The density of the solution is equal to 1 gram per mil, and the specific heat capacity of the solution is 4.19 joules per gram degree Celsius. So this piece here, this last sentence, there are 3 pieces of information that is usually made in calorimetry. One, there's no loss of energy. Two, that the density is equal to 1.00 grams per mil. And 3, the specific heat being 4.19 joules per gram degree Celsius. If ever you feel a question does not give you enough information, these are generally the assumptions that you can make. Because it's talking about losing heat to surroundings and it was a chemical reaction, we can look at this as a calorimetry question. And so we're going to look at our chemical system, which is our reactants. I'm just going to put reactants here. And our surroundings. And so when we look at this, a sample of ammonium nitrate having a mass of 30.5 grams is dissolved in water. That's the reaction. So mass is 30.5 grams. And it is made into a 500 ml solution. So the mass over here is actually going to be 500 mils. The heat of the solution, so that's going to be delta RH, is plus 25.7 kilojoules per mole. And then it says that the temperature of the water is 21.5 degrees Celsius. Determine the final temperature. So this is a great start. What we need to do is we don't have anything that works in milliliters. We need to multiply it by 1.00 gram per milliliter, which is the density, to know that we get the 500 grams. And that's where we told you 1 gram of water is equal to 1 milliliter of water, which is equal to 1 cubic centimeter of water. Over here, we need to pay attention to units. This is in kilojoules. So 25.7 kilojoules per mole multiplied by 1,000 joules in 1 kilojoule should give me 25,700 joules per mole. Okay? And so on the chemical side, we always have delta H. On the surrounding side, we always have negative Q. This is N delta RH, or N, remember I said this could be R. R just means the reaction. This happens to be a solution reaction. There's a combustion reaction. There's a formation reaction. This is equal to negative MC delta T. And so it's asking us to find final temperature. Delta T is equal to TF minus Ti. So let's just solve for delta T first and then go from there. So when we shift everything over, we're going to pull the negative with it because we want our delta T to be in a positive situation. We have the delta RH, it's 25.7 kilojoules per mole. We have the mass of the surroundings, which is 500 grams. We have the specific heat of the surroundings, which is 4.19 joules per gram degree Celsius. What we don't have is this mole piece. Mole piece from the chemical side is going to come from mass over molar mass. And so we're looking at 30.5 grams divided by the molar mass of NH4NO3. So we have 14.01, 4.01, 14.01, and 48. One nitrogen, 14.04, sorry. 4 hydrogens, 1 nitrogen, and 3 oxygens. And for that, we should get a total of 80.06 grams per mole. Okay? When we put it into M over capital M, N is going to be 0.38096 moles. So 0.38096 moles multiplied by 25,700 joules per mole divided by negative 500 grams multiplied by 4.19 joules per gram degrees Celsius. R delta T will be equal to negative 4.6734 degrees Celsius. And so delta T plus Ti will give us Tf, which means that we're going to go negative 4.7 plus 21.5 is going to be equal to Tf. It's going to be equal to 16.8 degrees Celsius. Okay? Okay. Aqueous copper sulfate reacts with sodium sulfate, or sodium hydroxide, in a double replacement reaction. A precipitate of copper 2 hydroxide and aqueous sodium sulfate is produced. 50 ml of 0.3 mole per liter copper sulfate is mixed with 50 ml containing an excess of sodium hydroxide. The initial temperature of both solutions is 21.40 degrees Celsius. After we mix the solutions in a simple calorimeter, the highest temperature reached is 24.60 degrees Celsius. Determine the enthalpy change for the reaction. Okay, so it says the word simple calorimeter. We know we're going to have chemical versus surrounding. Okay, when we talk about this particular sentence, 50 milliliters of 0.3 moles per liter copper sulfate is mixed with 50 milliliters containing an excess of sodium hydroxide. This goes back to Chem 20 when we talked about limiting and excess reagents. This one here, 50.0 mils of 0.3 molar copper sulfate, this is going to limit. That's going to limit the reaction, and so it's going to be the product that we use. So over here, we have a volume of 50.0 mils. We have a concentration of 0.300 moles per liter, and it's asking us to determine the enthalpy change. Now under surroundings, we need to look at two pieces. We took this simple calorimeter, and in it we had 50 mils of NaOH, to which we added 50 mils of copper sulfate. So our mass of our system is actually going to be 50 mils plus the 50 mils for a total of 100 mils. We need to remember that there's a 1 gram per milliliter density, so it's actually 100 grams is our mass. Our temperature initial for both systems was 21.40 degrees Celsius, and our final temperature is 24.60 degrees Celsius, and our specific heat is 4.19 joules per gram degree Celsius. And so delta H is always on the chemical side, negative Q is always on the surrounding side, and we know that this N delta RH is equal to negative MC delta T. It is asking us to find the enthalpy change, and so what we can do is we can just omit this piece because that is delta H and say that it is negative to MC delta T. So a little bit of extra information in here that we didn't need, and that's okay. When we recognize that delta H is equal to negative Q, we don't need this piece because we're actually solving for delta H. And we see that delta H is equal to negative 1340.8 joules, but we can't have 4 decimals. We're limited by our concentration. Even though we didn't do it, there's still only 3 sig digs. So delta H is equal to negative 1.34 times 10 to the negative, or positive, 3 joules, or negative 1.34 kilojoules. So you're going to pause it here and you're going to work through practice problems 1 to 5 and question number 13 on page 363 and page numbers 7 and 9 on page 355. Okay, when we're talking about simple calorimeters made of styrofoam cups, which is typically what they are, we don't need to account for the heat transferred to the styrofoam calorimeter because styrofoam is an insulator and it's not a transfer of heat. But not only that, when we look in our data booklet, we would see that water and styrofoam, not water, air and styrofoam have the same specific heat. Okay? But when we look at calorimeters like what we have in the lab, made out of metal, then we have to account for the heat because metal conducts heat. And so the enthalpy change for the reaction is equal to the total thermal energy. So a Q for the water or the solution and a Q for the metal. I'll show you what that looks like. 1.75 grams of octane is burnt inside a calorimeter. The temperature of 175 milliliters of water in a 12-gram aluminum calorimeter increased from 10 to 45 degrees Celsius. Assuming the water and the calorimeter both start and end with the same temperatures, what is the molar enthalpy change for the combustion of octane? So we're going to look at a chemical versus a surrounding. calculation. When we look at the actual specific chemical, the mass of octane is 0.75 grams. In the surrounding, we're going to have water, and we're going to have Q of the aluminum container. So here we have a mass of 175 grams. The mass of the container is 12.0 grams. And we know that the TF is 45 degrees, the TI is 10 degrees, and it's the same for both systems. The other piece of information that we need is the specific heat, so 4.19 joules per gram degree Celsius. And over here for aluminum, this is water. It is going to be, from your data booklet, you should see it says 0.897 joules per gram degree Celsius. And so delta H, which is what we find in the chemical system, is going to be equal to the total of negative Q water plus the negative Q of aluminum. So we have, and this is, we're looking for the molar enthalpy change of combustion of octane. So N delta CH is going to be equal to negative M water C delta T, all of water, plus M of aluminum, C of aluminum, delta T of aluminum. We're looking for the molar enthalpy, so all of that, whoops, I forgot the negative there. All of that's going to be divided by N. Now we have the information to figure out all these pieces with the exception of N. That's going to come from here, where N is equal to M over the molar mass. The molar mass being carbon is 8 times 12.01, and hydrogen is 18 times 1.01, and our molar mass is going to be 114.26 grams per mole, which means that our N is going to be equal to 0.75 divided by 114.26, and we get a value of 0.00656 moles. So then we can say delta CH is equal to negative, I'm going to put this in brackets, 175 times 4.19 times by 35 plus, I didn't need such a big bracket here, just a little bracket, 12 times all divided by 0.00656 moles for a lovely large number of 'When we go back to the question, we're only looking at 2 sig digs as being our limiting factor, which is this 3 and 9. So we get negative 4.0 times 10 to the 6 joules per mole, or negative 4.0 times 10 to the 3 kilojoules per mole. Okay. So we started out just learning about N delta RH. Then we moved into negative MC delta T, which is what we started working on at the beginning of the lesson, doing specific heat questions. And now we've moved on to looking at calorimetry, which is chemical versus surrounding. And we've compiled all of those two pieces together in this problem. So now you're going to pause the video and you're going to work on questions 14 and 17 as well as practice problem number 6 to get more practice at this.